Okay, hi everyone. So let's start. Any question before we start about assignment, the course? What?
I have lots of questions.
Yeah, feel free to ask. And by the way, if there is anything private, you can ask me privately when you message me. But if it's not private, it's better to ask it in the group so everyone can see the answers. I don't know why people prefer to ask questions privately, but it would be better, also more fair to other students, because then everybody will be able to see the answer. This might be the question of others too. So that's one thing. And feel free to ask me any questions if you have about anything. No questions so far? Okay. So we continue where we had left off. So we were talking about RNN and LSTM. Now, so we talked about gradient vanishing or explosion in long-term dependencies. You remember we said that RNN tries to learn the dependencies of the data points in the sequence, and so it considers a window, and in this window we will capture both short-term and long-term dependencies, right? And the more we go in depth in the window, the more long-term dependencies we are learning. Okay, but we said there is a problem with long-term dependencies, and that is what? There's a problem with that, and that is multiplication of a lot of gradients with each other through time. Therefore, we'll have either gradient vanishing or explosion. Why? Because if we have a lot of small gradients, a bit smaller than one, then their multiplication becomes too small. Or if they are a bit larger than one, then their multiplication can explode. Okay, we had already talked about it in these slides in the previous session. And then we said, we have the problem of gradient vanishing or gradient explosion in long-term dependencies, usually gradient vanishing. Right? So we said that we need to tackle this problem with several solutions, some of which are these. So one of them is close to identity weight matrix. What do we mean? So do you remember equation 4 that we had in RNN? What was it? It was, so this was IT, right? WHT minus 1 plus UXT plus BI. But after we pass it to a hyperbolic tangent activation function in order to get the HT, the hidden state at the time t, right? And that is between -1 and 1. Why? Because hyperbolic tangent is in the range -1 and 1. Okay. And as this shows, the state is multiplied by a weight matrix W. So here we have HT minus 1, it's multiplied by W at every time step. And if there is a long-term dependency, many of these W matrices are multiplied to each other, right? So why? Because of the recursion. So we have HT minus 1 here multiplied by W, but this HT minus 1 can be written as the hyperbolic tangent of W HT minus 2 plus UXT minus 1 plus BI, right? Then if you write it recursively, you will see a lot of W's will be multiplied by each other. So now let us work on the matrix W in order to resolve the issue of gradient vanishing. So what do we do? Suppose the eigenvalue decomposition of the matrix W is this: A lambda A transpose. Recall preliminaries. Okay, where A are the eigenvectors, so the columns of A are the eigenvectors of W, and lambda is a diagonal matrix having the eigenvalues of W. Okay, then what do we do? Let's replace this W with its eigenvalue decomposition in equation 4. So we will have A lambda A transpose times HT minus 1, etc. Okay, Now it says if a change epsilon, so a change small, in some element of the state HT-1 is aligned with an eigenvector of the weight matrix W, then the effect of this change in HT will be lambda T epsilon. So this T is not transpose. This T is the power of T, okay? After T time steps. So why? What do you remember? Here we have multiplication of the eigenvector A, the column of eigenvector with HT-1. Do you agree? Do you agree? Okay, then what happens? After T time steps, we have a T times of the multiplication of W by H, right? Therefore, we have T times of multiplication of eigenvalues with the H. And eigenvalues are lambda. So we have lambda to the power of T, okay? Because we have lambda times of the multiplication. So lambda to the power of T times epsilon, right? As we have it here, after T time steps, according to equation 24 here. Then two cases might happen. What? If the largest eigenvalue is less than 1, so lambda is less than 1, then what happens? Then the change lambda to the power of T epsilon is contrastive. It means that it goes down because lambda to the power of T becomes too small, right? If lambda is less than 1, then lambda to the power of T for large T goes very small for long-term dependencies. In this case, gradient vanishing occurs, right? For in long-term dependency. And network forgets very long time ago. Okay. However, in the second case, if the largest eigenvalue is greater than 1, then the change lambda to the power of T epsilon is diverging because lambda to the power of T becomes too much large for long-term dependencies. In this case, the gradient, we have gradient explosion. The gradient network forgets very long time, sorry. In this case, I apologize. In this case, gradient explosion occurs in the long-term dependency, and remembering very long time ago dominates the short-term memories. So in gradient vanishing, we forget the long time ago. In gradient explosion, it dominates for us to remember a very long time ago. So we forget short-term ago. Okay, do you get it? Both are destructive. We want to learn both long-term and short-term dependencies. That's one thing. By the way, why am I saying largest eigenvalue? Because this is the worst case scenario, right? When the largest eigenvalue is less than 1, all of the eigenvalues are less than 1. When the largest eigenvalue is greater than 1, I think this, the largest eigenvalue is a dominating eigenvalue. That's the reason. Okay, now, as remembering short-term memories is usually more important, of course, it is more important to learn to remember short-term memory than long-term memory. Why? What is the reason? It becomes a bit philosophical because natural language processing is very related to the philosophy, analytical philosophy. Do you know anything about the philosophy? Okay, so philosophy can be categorized into two broad categories. One of them is continental philosophy, and the other one is analytical philosophy. Analytical philosophy started since the start of last century, okay? By who? Russell, you know Russell, right? Russell and Frege and Moore and Wittgenstein, okay? These are the famous philosophers in the previous century. So they started some hot topic in philosophy. Do you know what they said? So previously, continental philosophers such as Kant, such as Descartes, such as many previous people, they said they always thought that language is just a means for transferring what you're thinking, okay? But listen to this. This is important for understanding natural language processing. So continental philosophers, they always thought that we think, and then in order to transfer it to others, we just use language. However, some people, as I said, Russell, Frege, Moore, and Wittgenstein, they said, no, we can't even think without language. We use language in order to think. Baby, for example, a baby, without knowing any language, it can't think. It starts to learn thinking by learning language. Can you believe that? A newborn baby can't think. At first, it learns the words and then the sentences, and then it starts the patterns of thinking. Okay. I think you also understand if when you are thinking about anything, you are using sentences in your mind. Okay, that's one thing. So I think Frege, have a principle of context. Frege or more, but I think it was Frege. Has a principle of context in language. What? Yes, so someone here, for this to be recorded, someone asked, we also think in images. Yeah, that's another thing which was proposed by Wittgenstein. Yeah, I think it was early Wittgenstein, because we have early Wittgenstein and later Wittgenstein. Early Wittgenstein said that yes, there is we think with like images. So yeah, the meanings are like images in a world of logic. So in the Tractatus, take a look at logico-philosophical Tractatus of Wittgenstein. Take a look at that. You can find out that he talks about this. But later, Wittgenstein refused this idea. He rejected himself and said, no, apparently we choose the languages, the words of the language based on the context. So early Wittgenstein, as you see, it's very related to natural language processing. Early Wittgenstein said, the words, the concepts are in a world of logic. We just use them, okay? However, later Wittgenstein said, no, we choose the words based on the context. So for the functionality of language, we choose the words. For example, he said, I talk differently when I'm talking in academia, while when I'm talking to a car dealer. So you choose different words in different situations. So this is how, but yes, I'm saying that these are different theorems how should I say, different ideas for use of language in analytical philosophy. This is how much I know, but I know that, yes, so some of the ideas say that we think by pictures. Some of the ideas say that we think by language, but Wittgenstein said language is the picture, actually. Language is the picture. You can see the language as a picture. This is what early Wittgenstein said, as much as I know. Okay. Yes, so you're saying that there is a disease named dyslexia, okay, that they think within images. I think I also saw a documentary about Einstein. Einstein had probably this disease or a similar disease. He thought in music notes. So whenever he had a problem, he played violin in order to think. And in the middle of playing violin, he would come up with his ideas in theory of physics. Okay, so people but you can see music notes is also a language. So everything you can see it as a language. Either it must be some language, either music notes or image or English language, Persian language, Arabic language, whatever, right? You need to have some language. It might be music in order to think. That's the thing. That's the idea. But as I was saying, there is a principle of context a century ago, proposed, saying that the words are connected to each other based on the context. So, and as we see, natural language processing is all about this. Words are related to each other. Well, short-term memory. So in short-term memory, because the closer the words to each other, the more related they are to each other. Because the more apart they are from each other, there might be less related to each other, right? This is what NLP is about. Also, we will see in this session that attention mechanism which is the state of the art for NLP, is based on analytical philosophy. That also says how related the words are to each other, how related the words, how each word is attending to other words. Can you believe it? So yeah, there is a big connection between natural language processing and analytical philosophy. Okay, let's go back to where we were. So remembering short-term memories is usually more important than remembering very past time in different tasks. It is recommended to use the weight matrix W whose largest eigenvalue is less than 1. You remember? So as we talked about, if it is greater than 1, then long-term ago dominates, right? But we want to learn short-term memories. They are more important, so they should be less than 1. However, they shouldn't be too much less than 1. If the largest eigenvalue of W is too much less than 1, then we completely forget long time ago. Very soon, okay? So it should be a bit less than 1 in order to not forget long time ago, but also remember short term ago, not to be dominated by long time ago, right? So that's the thing. Okay, this makes the RNN have the Markovian property. Do you remember? We talked about it. Markovian property. What does it say? It says that this state only depends on the previous state and not much time ago, because the previous state also depends on its previous state. So, okay. And however, if the largest eigenvalue of W is much less than 1, gradient vanishing happens, and we forget very soon ago. So it happens very sooner than expected. Okay. Therefore, it is recommended to use a weight matrix W whose largest eigenvalue is slightly less than 1, right? This makes the RNN slightly contrastive, slightly. Okay. One way to have the weight matrix W whose largest eigenvalue is slightly less than 1 is to make this matrix close to the identity matrix, right? If it is identity matrix, it means that its eigenvalues are 1, right? So close to identity matrix. There exist some other ways to determine the weight matrix W. For example, the weight matrix can be set to an orthogonal matrix. So reference 30 has done that. So there were a lot of papers saying that what we can do with the weight matrix W. Okay. Another approach is what? To copy the previous state exactly to the current state. In this approach, equation 4 is modified to this. So what do I mean? Here. So if you drop this term, it will become the previous equation, right? However, I'm adding or copying the previous state again. And what does it do? So if you consider these two together with the additional term, then you factor out HT minus 1, right factor out. So you will have W plus I. What is W plus I? So it's strengthening the main diagonal of W, right? Do you remember, especially when it is, you encounter this a lot in machine learning, especially when you want to take an inverse of the matrix. So you strengthen the main diagonal a little bit. What does it do? It makes the matrix full rank, right? Okay. This prevents gradient vanishing because it brings a copy of the previous step to the current state. This can be interpreted as strengthening the diagonal of the weight matrix, hence increasing the largest eigenvalue of W for preventing gradient vanishing. Also, you can see it in another way. In backpropagation, you're having another way, just a shortcut to the previous state, right? Therefore, the gradient flow is better. Therefore, it prevents gradient vanishing. Okay, so you can say also gradient flow better will become better. Shortcut. So as equation 4 and the figure of RNN show in the regular RNN, so another technique. So close to identity matrix was over. Now long delays. Okay, it's another technique. What do we do? In the regular RNN, every state HT is fed by the previous state HT minus 1, as also shown in this figure, right? Through the weight matrix W. So here we have W, W, W. As discussed before, in the regular RNN, the effect of the change epsilon in the state results in this lambda to the power of T epsilon. We already talked about it, right? After T time steps. where lambda is the largest eigenvalue of W. Okay. Then in the regular RNN has one-step connections or delays between the states, right? As you see, these are one state. It is possible to have longer delays between the states in addition to one-step delays. I think I have the figure here. I hope I have it. Yeah, I have it. For example, here we can. What is this? So these delays is one step delay, but these delays are 1, 2, 3, 3-step delays, right? So we can have longer delays also. So that's one technique. In other words, it is possible to have higher levels of Markov property, right? Rather than only one level of Markov property. So let WK, so what is it mathematically speaking? Let WK denote the weight matrix for the K-step delays between the states, right? So previously when we only had W, now we have W1, W3, whatever. So WK means the K steps before. Okay, then we can have this. So we'll have a summation of WK HT minus K, where we are using the K steps before, okay? Where the summation is over the K values for the existing delays in the RNN structure, okay? An example for RNN network with 1-step and 3-step delays, right? So we denote them by this 1 step, this means 3-step delay. So if you unfold it, it becomes like this. You see that? Here we have W1 for 1-step delay and W3 for 3-step delays, right? And this is shared between them, between the states. Do you remember? We also talked about it. The weights are shared in order not to have overfitting, okay? Then I think you find out why it is helping. Why? Again, it's kind of a shortcut for gradient flow in backpropagation. So we will not have gradient vanishing. So one analysis is shortcut. Another for gradient flow. Another one, you can see this, having long delays in RNN is one of the attempts for preventing gradient vanishing. This is because every state is having impact not only from the previous state, but also from the more previous states. Or in other words, we have shortcut. Therefore, in backpropagation, we have some skipping gradient flow from a state to more previous states, right? So this means that we have less number of multiplications in gradient. So gradient vanishing doesn't happen. Okay. Another technique is leaky units. Leaky units. So references 11 and 12. Let HTJ denote the jth element of the state HT. Okay. So do you remember HT is p-dimensional vector. So let HTJ be the jth element of the vector HT. Okay. Then in leaky units, equation 4 is modified in this way. So we have HTJ 1 minus 1 over Tj, Ht minus 1 and J. So this is the jth element of the previous state, and 1 over tau J, tangent, hyperbolic tangent of this. So this already we had it before, but now this is for the jth element, okay? And Wj double dot means the jth row of W, okay? Uj double dot is the jth row of U, Bij is the jth element of Bi. Okay, and tau J is between 1 and infinity. So basically what it is saying, it is saying, let's have a linear combination of what we had before and a new term. And what is that new term? The previous state. So let's have a linear combination of the update that we had before and the previous state. What does it remind you of? Very similar to the idea of momentum. A log of previous states, okay? A log of previous. So very similar to idea of momentum. So when tau, let's analyze it. When tau J is 1, what happens? Then this equation becomes this, which gives back equation 4 as in a regular RNN. However, when tau J is much greater than 1, what happens? Then it becomes the previous state. So it's a linear combination of both extreme cases, okay? Then the larger the tau J, the easier the gradient propagates for HTJ, HTI, HTJ, I think. Therefore, by tuning TJ, it is possible to control how much of the path should be directly copied and how much should be passed through the weight matrix. Do you agree? So if you set tau j to 1, it becomes just updated through the weight matrix W. If you set tau j to be too large, then it's exactly the previous state. So by controlling tau j, you can see how much you want to use W weight matrix and how much you want to copy from the previous state. Okay. Then also, it is important that different tau j's, the leaky units use different tau j's. Wasn't it a question for you? Why am I using tau j? Why aren't I using this formula for the whole HT? Wait. HT is a vector, right? Here, equation 27 is element-wise. Why? Because we want to have different tau j's for different directions, right? Why? Adam also had kind of linear combination. Yes, the ideas are very similar because Adam was also using momentum. Do you remember? Kind of momentum. So yeah, the ideas are very similar. It's very similar to the idea of Adam. The ideas are repeated a lot in machine learning. But the question is, why am I using tau j for the jth element? This is because I want to treat the elements differently. I don't want to see the whole elements directions the same. So I let backpropagation decide about the p directions of the states separately. Okay. Okay. So if you can let tau j to be learned by backpropagation, or you can set it by yourself manually. Anyways, you are treating them differently. Okay. If you set all of the tau j's equal to each other, then you are treating all of them the same. But not all of the directions are the same because sometimes you want to forget some directions, and if some directions we don't want to forget. We want to keep some of the directions, right? And as you see, why do we call them leaky units? Because we have a leak of previous state, as done in equation 27. A leak of information from the previous state, right? Another technique is echo state networks. Echo state. These are families of networks which came during years. So one of the approaches to handle the problem of gradient vanishing in RNN is to use echo state networks. References 13 and 14. These networks consider the recurrent neural network as black box having hidden units with nonlinear activation functions and connections between them. Okay, so you can see it as this here. This is black box of recurrent neural network. You have various connections to each other, and you have a lot of recurrence in this box. So you see it as a black box. And interestingly, it says, I don't want to learn the weights of this black box. I let them to be fixed. Okay. And it calls this black box reservoir dynamical system. This is the name that the author chose. Okay. Reservoir dynamical system. And then it said, let's add a learnable weight, one linear layer at the end, and learn those weights. So the weights of the last layer will be learnable, okay? But the weights in the reservoir dynamical system will be fixed. What does it remind you of? This is the idea of transfer learning. So what is transfer learning in deep learning? So assume you train your neural network with some data set, okay? Then after a while, you will see that your data has a shift in domain. So you will have a domain shift in your data, okay? It might be the domain shift in training, the new training data, or it might be domain shift in test. Doesn't matter, you have some domain shift. If you feed that to the already trained network, it will work awful, right? Because the network was trained on the previous domain, okay? Then you need to fine tune the weights for the new domain. How do you do that? There are several ways. You can do several iterations of backpropagation, several, by the initialization of the weights trained in the previous data set. So you don't start from scratch. You already have the weights which were trained on the previous data set, okay? And from that initialization, you fine-tune your weights for the new data by several iterations or epochs of backpropagation. Why am I saying several epochs? Because if you do it a lot, it completely forgets what it had learned before on the previous dummy. You don't want to forget the previous data, okay? Also, you don't want to, in other words, you don't want to get overfitted on the new data. Okay, that's one thing. So there are several ways to do transfer learning. One way is that you completely fine-tune all of the weights in your network. Another technique is that you freeze some of the weights. Usually, you train on the very last layers in the network, okay? And these very last layers might be added later, or there might be the actual very last layers of the previous network. Why do you do that? First off, for the computational resources, you don't want to train the whole thing from scratch. So you just fine-tune some last layers, okay? Because training the whole network is very time-consuming, resource-consuming. That's one thing. Another thing is that you don't want to touch the weights which were trained before. You just want to fine-tune some of them, okay? A subset of them. This is one thing. For example, this network might be trained by big companies. So the weights are important. They have used a lot of servers to train them. Let's not touch them. Let's just fine-tune some of the last layers, okay? And as you see, the idea is very similar to transfer learning. Maybe this was the idea which where the transfer learning was inspired by, right? This is a very old network. Okay, so we have a last layer learnable weights, and it uses mean squared error as the last layer is fully connected without any activation function at the end. So what does it mean? It's a linear projection, right? It's a linear projection. And after that, we are using mean squared error. What does it remind you of? If you have watched my lecture on regression in the statistical machine learning, this is exactly linear regression. So it's learning the weights by linear regression. If you learn the weights by mean squared error using gradient descent, you will end up with the solution of linear regression, okay? Then, because of not learning the recurrent weights in the reservoir system and sufficing to learn the weights of the output layer, then we don't have gradient vanishing. So we had a problem, it completely erased the problem. It didn't try to resolve the problem, it completely erased it by saying that I don't learn the weights in the reservoir system, okay? A tutorial on this topic is reference 32. Okay, now LSTM, long short-term memory networks. So as examples in introduction showed, we need short-term relations in some cases and long-term relations in some other cases. Do you remember in the previous session, we talked about two examples where we had needed short-term and long-term relations. Okay. RNN learns the sequence based on one or several previous states, okay, depending on its structure and the level of its Markov property. That is the figure for the RNN, which we already saw before, unfolded one, okay? Therefore, we need to decide on the structure of RNN to be able to handle short-term and long-term dependencies. Why? What do I mean by this? The size of the window determines how long time ago I want to learn in RNN. Also, when the window becomes too large, we have the problem of gradient vanishing. So we need to change the structure of RNN as we talked about it, like leaky units, like longer delays. We already talked about this, right? So we modify RNN manually. Then someone said, why do I modify it manually? I train a network to learn it itself. How to modify the network in a way that it learns long-term dependencies if required. It learns short-term dependencies if required. Let the network learn it by backpropagation itself. And that's the idea of LSTM, okay? So instead of manual design of RNN structure or deciding manually when to clear the state, we can let the neural network learn by itself. And that's long short-term memory, or LSTM, initially proposed in these references in 1995 to 1997. It does that. It learns from its input sequence when to use short-term dependency, that is when to clear the state, or when to use the long-term dependencies, that is when not to clear the state. Okay. So LSTM, what is it? It consists of several cells. So we have several cells in LSTM, which are repeated, each of which corresponds to a time slot, right? So we have several time slots, and each corresponds to one of the time slots. Every LSTM cell contains several gates. So we have cells, and in each cell, we have several gates for learning different aspects of the input time series. So you can see, for example, here, what is this? Xt minus 2, xt minus 1, xt. This is the input sequence, right? In time t minus 2, time t minus 1, time t. So we have yt minus 2, yt minus 1, yt. These are the outputs, right? The output, for example, it might be prediction of classification, regression, whatever. Okay. For example, we want to see whether this word is appropriate or not, whatever. So we can have a classification, regression, but it depends on our task. And we have CT minus 3, CT minus 2 between the cells. Also HT minus 3, HT minus 2, etc. between the cells. So H's are the states, hidden states. We also have an additional signal named C. We'll see that, okay? So this is the picture of one of the LSTM cells. So inside the LSTM cell, if you zoom, you will see this. Okay, so we have CT minus 1, HT minus 1 as input. We have XT as input. So this is the input sequence, but these are the states between the cells. This is YT output. And we have 4-gate gate, input gate, new memory, and output gate. Okay. So let's see that. Let's talk about input gates. One of the gates in the LSTM cell is input gate, first proposed in, so by the way, the gates were proposed in different papers. Okay. So LSTM cell was improved gradually. So it was proposed in references 15 and 16, I think the original papers of LSTM. This gate, what does it do? Takes the inputs at current time slot, xt, and the hidden state of the last time slot, or the previous one, ht minus 1. Okay, it takes these two and outputs the signal it, which is a p-dimensional vector, and it is this. So wi, I have wi, ht minus 1. By the way, these wi's, ui, pi, and bi, these are learnable parameters. Okay, these are learnable parameters by backpropagation. So wi is p by p, ui is p by d. Note that xt is d-dimensional. Okay, ui is p by d, bias is p-dimensional. Then these are the learnable weights for the input gate. What is this notation here? This is Hadamard product. These terminologies, trying to learn them. Whenever you write a paper, rather than saying, for example, if you multiply 2 vectors or 2 matrices element-wise, don't say it element-wise product. Call it Hadamard product. So say, okay, Hadamard or element-wise product. Then, so it basically means pi times element-wise times CT minus 1. By the way, you might be wondering, why aren't I saying pi transpose CT minus 1? Because inner product also multiplies the elements by each other. There is a difference between Hadamard and inner product. In Hadamard, you don't sum. So you have element-wise product, but you don't sum them. So the output of Hadamard product is the same as its dimensionality is the same as the dimensionality of input. But in inner product, the dimensionality becomes a scalar, right? Do you see the difference between these two? Okay. So here we have ht minus 1 times multiplied by wi, xt multiplied by ui, I have CT minus 1 from the previous cell times PI, which is learnable, and also some bias, BI. As you see, it's very similar to the idea of RNN. RNN had very similar thing, right? Equation. And by the way, CT minus 1 is the final memory, so it's called final memory of the previous time step, which will be explained later, okay? And PI is p-dimensional. It is the learnable p-pole weight. So it's called p-pole weight, reference 33, okay? Letting a possible leak of information from the previous final memory. So what do I mean? Take a look at this figure, which is larger. So PI is a connection from CT minus 1 and comes here. So it means that I can have a leak of information from CT minus 1. It's optional, but it helps. Maybe we need some leak of information. Let the network learn that, okay? So that's the thing. It's called peephole because it's like a peephole for seeking into that. Okay, and the function this sig, which is between 0 and 1, this is sigmoid function, the activation function, okay, which is applied element-wise, and this is sigmoid function. So we have nonlinear activation functions in order to learn the nonlinear patterns of data, okay? So this was input gate, and also, so I'm repeating this here, as this equation demonstrates, the input gate considers the effect of the input and the previous hidden state. So xt, the input at this state, at this time, and the previous state. It controls how much I should use the xt and how much I should use ht minus 1, okay? It may also use a leak of information from the previous memory through the people, right? Leak of information from CT minus 1, okay? This gate carries the importance of the information of the input at the current time slot. So how much the input xt is important with respect to ht minus 1. If it is important, then ui gets large and wi gets small. If it's not that much important, ui is small, wi is large, it means that copy the previous state, okay? So that's why we call it input gate, hence the name input gate, okay? Now forget gate. Another gate we have, the second gate is forget gate. So what does it do? So here, by the way, in this figure, I should tell you, in this figure, I have a mistake in my notation. So this is PF, this is PI. I think it's obvious because PI goes to the input gate and PF goes to the forget gate. Doesn't matter, okay? So, as I said, another gate in LSTM cell is forget gate, proposed in reference 34. It wasn't in the original LSTM paper, okay? This gate also takes the input at the current time slot xt and the hidden state of the previous time slot ht minus 1 and outputs the signal ft p-dimensional. So it is a p-dimensional vector. And also we have bf as the bias, p-dimensional. You have wf, uf as the learnable parameters. We have ht minus 1 xt. We have another p-pole weight denoted by pf, element-wise Hadamard product with CT minus 1 in order to see letting a possible leak of information from the previous final memory. But you might have a philosophical question here. It's very similar to the input gate. Why do I have that? Because they have separated these. Why? Although they are very similar, but maybe so first off, it adds more parameters to learn. Okay, the more parameters to learn, the more nonlinear patterns of data you can learn if you have enough data to train. Okay, if you don't have enough data, you will get overfit to the data. Okay, that's one thing. So they're adding parameters for learning the patterns of data. Also, input these gates, although they are very similar, they can play some role in the responsibility. Do you remember in convolutional neural networks, we had several filters of the kernel. the same philosophical question could have been raised there, saying that why do we need several filters, several channels, several filters of the kernel? Because each of the kernels in the convolutional neural network will take some responsibility in our task. For example, one of the kernels in the filter bank says that, okay, I will learn the edge at the right corner, but the other kernel will say, no, I will learn, okay, you learn that, I will learn the bottom corner, okay? So that's the idea. The forget gate, what does it do? It considers the effect of the input and the previous hidden state and perhaps a leak of information from the previous memory. Okay, that's obvious. This gate controls the amount of forgetting the previous information with respect to the new coming information. Again, it plays with WF and UF to see how much it should use XT with respect to HT minus 1. Should I forget the previous? What do I mean by forgetting? If you set WF to be small, then it means that you forget the previous state, the previous data. Okay. But then we have output gate. What does it do? Proposing 15 and 16 in the original paper of LSTM. This gate takes the input at time t, also state at previous time, and outputs OT. Okay. Here, again, very similar to the previous gates. However, as I said, it plays another role in the LSTM cell. So we have different roles. So the effect of the input and the previous hidden state are considered, and also a possible information leak from the current memory. I think from this cell, you can also see that they're very similar, these gates. Let me bring the big large. So here, this is the output gate. This is the input gate. This is a forget gate. Naming is not important. Mathematics is important. You can see Benjamin, 1 Benjamin, 2 Benjamin, 3. So you have 3 repeats of Benjamin, but with different weights. So each of which will do something. Okay? They will play around with their W and U in order to take some responsibility. That's one thing. Okay. But in order to make it fancy, they named it forget gate, input gate. Okay. So new memory cell, also called block input. What does it do? The LSTM cell has new memory cell, and this gate takes the input at time t, xt, the hidden state of the last time state, ht minus 1, and outputs the signal ct tilde, which is a p-dimensional vector. Okay. Then what does it do? This gate considers the effect of the input xt, the previous hidden state ht minus 1, and to represent the new information of current input. So there is a difference. Here we don't have any p-pole. Okay. And again, we have WC, UC, BC as learnable parameters. Okay. Here, another difference is that the activation function is hyperbolic tangent. The previous ones, it was sigmoid. Okay. What is the difference? Hyperbolic tangent lets it between -1 and 1. Sigmoid is between 0 and 1. Okay. The new memory cell is also referred to as a block input in the literature. So different names for the same thing. The signal CT tilde is sometimes denoted by ZT in the literature. Different notations for the same signal. Okay. So if this is the new memory cell. Now we have the final memory calculation, which is CT. So CT in this figure is here, CT. So what is it? It gets the outputs of the input gate IT, the forget gate FT, and the new memory cell CT tilde. It uses them in order to calculate the CT, which is a p-dimensional vector. It's called final memory. Okay. So what does it do? It uses the Hadamard product or element-wise product of FT and CT minus 1. Also, Hadamard product between IT and CT tilde. And I will see the interpretation. I will tell you the interpretation. First off, let's take a look at the figure. What does it do? So here it is. IT, so see, IT is here, and CT tilde is here. They are multiplied by each other, Hadamard product. So this is this term. What is FT? FT is here. CT minus 1 is here. Hadamard product. So we have it here. This is this term. We add them. It gives us CT. Right? Now let's interpret it. So what? First off, it takes the effect of the forget gate, the previous memory, the input, and the new memory, all of them. It aggregates the effects of these. Then what does it do? In the first term, FT times CT minus 1. What does it do? The forget gate controls how much of the previous memory CT minus 1 should be forgotten. As I said, FT is a forget gate times CT minus 1. How much should I forget? So FT can handle forgetting in two ways. Let's go back to FT. First off, it has WF in it. So if WF is a small, the effect of HT minus 1 is reduced. In this is one way of forgetting. Another way of forgetting here is FT is multiplied, the output of FT is multiplied with CT minus 1. Also, another signal from the previous memory. Okay, that's one thing. So the second term now, IT times CT tilde. But it controls how much of the new input information should be used. Why? Because IT is the information of input, right? Input key. And CT tilde also, if it is a small, we don't use IT. If it is large, we use it. Again, in two ways, IT is being controlled. IT has in it, has WI, I think. Yes, WI. Where was that? Here, WI and UI. So if UI is large, it uses XT. If UI is small, it doesn't use XT with respect to HT minus 1. Also, at the same time, I'm multiplying the output of input gate IT by CT tilde. Means that I can control it by CT tilde also. Here, where was that? Here, by CT tilde. Okay. So now we aggregate these two effects and it gives us CT, and it goes to the next cell. So we had this. It determines a trade-off of usage of old versus new information, right? Do you agree? So both of these terms are kind of considering the trade-off of usage of old versus new information. The weights of these gates are trained in a way that they pass or block the input or previous information based on the input sequence and the time step in the sequence. Okay? So based on the data itself and also the time step that we are, it finds out whether it should reduce the effect of the new information or increase it. In other words, for example, you have a sequence. Maybe in the first hour of your sequence, long-term dependency is very important. It learns that. But after a while, gradually, we have a domain shift, and short-term dependency is more important. It changes. During the backpropagation, it changes the weights in order to forget the previous information. So it depends. It's a flow in the air. How do I call it? It is based on the stream of data. Okay. Okay. Now the hidden state. So we have one other thing in this cell, which is HT. The hidden state, also called block output. So hidden state is a p-dimensional vector between -1 and 1. It is defined as the Hadamard product or element-wise product of OT, output gate, and the hyperbolic tangent of CT. So in this figure, you can see hyperbolic tangent of CT times OT. It gives me HT. Okay, so you can see that HT, this is called hidden state. It is also called block output. And it goes to the next cell in order to be used. It was used a lot in all of the gates. Do you remember? We have also output, YT here. What does it do? The output YT, which is Q dimensional, it is defined as VHT plus BY. So we might have some bias and some learnable parameters V times HT. Okay, interestingly, usually in the literature, you might see that in this LSTM cells, rather than YT here, we have CT. Do you know why? They don't write any YT. So they consider CT to be output because they are taking V to be identity matrix and BY to be 0. So YT becomes HT. Sorry, CT. Sorry, HT. They sometimes call it HT. Oh, yes. This HT, they also denote the output by HT. So they are simply setting V to be I. Okay. When I was writing this tutorial paper, because this is based on my tutorial, I was very confused. Where did YT go in the shapes that people are drawing? And I found out that V should be I in those cases. We had a discussion with Professor Otzi on this, I remember. Okay, history and variance of LSTM. Okay, so LSTM has gone through various developments and improvements gradually. Okay, so for the history of LSTM, you can see reference 35. That's a very, very good paper. Some of the variants of LSTM do not have peepholes. Okay, some of them don't have peepholes. In those, usually, actually, we don't have peepholes. And then the equations of the gates are simplified in this way. So you see them a lot in the literature, IT, FT, and OT. So we don't have any peephole terms. Okay. Then let's review a history of variants of LSTM. So LSTM was originally proposed by Hochreiter and Schmidt-Huber in years 1995 to 1997. Okay. We call it original LSTM. Okay. Then the original LSTM had only the input and output gates. It doesn't have 4-gate gate and other gates. Okay. So only input and output gates introduced before. And it did not have a 4-gate gate. Did not have a 4-gate. Okay. It also did not contain the peepholes. Therefore, the gates were simplified to the equations that we had. Then the original LSTM trained the network using backpropagation through time, which we talked about. Okay. And a mixture of real-time recurrent learning. For more information, see references 2 and 4. But backpropagation through time is the main algorithm for training that. Later, Gers et al., references 34 and 33, applied some changes to the original LSTM. And we call it vanilla LSTM. Okay. So what does it do? The 4-gate gate, it was proposed for the first time in reference 34 by Gers et al. To let the network forget its previous states, either completely or partially, right? Then the peephole connections, they were first proposed in reference 33. 4-gate gate, which was proposed in 34, now it is used a lot. However, peepholes are forgotten in reference 33. Okay. 5, the peepholes were for possible leak of information from previous or current final memory. These two papers also incorporated the full gate recurrence, which is these equations, we'll talk about it, in which all gates receive additional recurrent inputs from all gates at the previous time step. So we have additional terms. What are these? We have these. So it means that so far we only talked about these terms here. However, all of these are added. So using some learnable parameters, R, RRI, RII, RIF, RIO, RFI, doesn't matter, okay? All of these parameters, you have some learnable parameters. These, by the way, do you know what this means? It is a fully connected layer, right? By the way, it's RII. We already talked about it. These are just fully connected layers. You don't need to worry about that, which take inputs for IT minus 1, although the layer is RII transpose, okay? Right? And so these are nothing very complicated. These are just fully connected layers. Yeah, then you are taking the output of IT minus 1, FT minus 1, OT minus 1, and bring it inside for the sigmoid for IT. So for IT, FT, and OT, you get all of the outputs of the IT, FT, and OT from the previous time slot. And you learn them. So why do they do that? They want to add additional parameters, but they know that they have enough data to train them. Why? In order to handle nonlinearity better. Okay. However, this disappeared in the later papers on LSTM. So they found out that it's useless. Okay. Later, Graves and Schmidt-Huber adapted the original LSTM and proposed vanilla LSTM in 2005. Sorry, that wasn't vanilla LSTM. I apologize. 33 and 34 was some other thing, improvement over original LSTM, but it developed into vanilla LSTM in reference 18, which is one of the most common LSTMs in the literature nowadays. Okay, the vanilla LSTM incorporated the structures of original LSTM and the papers 33 and 34. So a combination of original LSTM and references 33 and 34. The full backpropagation through time introduced before was used for LSTM in vanilla LSTM. Okay, so they use backpropagation through time for training. Then other LSTM variants. Let's talk about them very fast. There are other variants of LSTM, although most common used LSTM is vanilla LSTM. So backpropagation through time was used for training in reference 18. However, Kalman, there are some other techniques for training LSTM, such as Kalman filtering. You can see the references for them. Another one is evolutionary learning. Do you know what is that? This is just a voice search. Have you heard of genetic algorithms, for example? So in optimization, in classical optimization, you use gradient and these things in order to move toward the solution, right? Like gradient descent and these things. However, sometimes two cases might happen. Either the cost function is too complicated, too highly nonlinear, or you are lazy, you don't want to use gradient and mathematics. So you want to just search. Rather than a DOM search or a grid search, which is very bad in time complexity, you do a voice search. So usually you have some particles, and these particles talk to each other in a way that mathematically talk to each other in a way that, okay, I found a better solution, so all of you come toward me. Okay, so kind of a voice search. And some examples are genetic algorithms or particle swarm optimization and these things. Okay, so using these, you can search for better weights in the neural network, right? So one of the ways to learn neural network is search of the weights. So evolutionary learning. Another one is context-sensitive evolutionary learning. Finally, in 2014, this is important. One of the biggest improvements of LSTM was proposed, which was gated recurrent units, GRU, proposed by Benjou et al. At the University of Montreal, right? So what did they do? The philosophy of GRU was this. Let's simplify the LSTM cell. It's too complicated. We don't need too much parameters. Why do we need that? It overfits. Okay, let's simplify that. In other words, GRU raised the question of whether we need to be that flexible like LSTM to learn the sequence. Maybe a simpler network can learn that. Okay, so let's simplify LSTM. Less flexible than LSTM, but good enough for the sequence learning. Okay. GRU, or gated recurrent units, redesigned the LSTM cell by introducing, now they have their own gates. What are they? Reset gate, update gate, new memory cell. Therefore, the number of gates were reduced from 4 to 3. Okay. It was empirically shown in reference 14 that the performance of LSTM improves by using GRU cells. Otherwise, their paper would be rejected, right? Later in 2017, the GRU was further simplified. So this is the second version of GRU in 2017, reference 41, by merging the reset and update gates into a 4-gate gate. So people were just playing around with the gates in order to have new papers, right? So nowadays, GRU is the most commonly used LSTM structure. Okay, let's see. We go into GRU now. Gated recurrent units, or GRU. This is the GRU cell. Take a look at that. The main GRU, so as I said, we have two variants of GRU. We see them. The main GRU was fully gated unit, reference 17, whose gates are introduced in the following. Okay, so take a look at this because we are gonna go into the equations. So we have reset gate here, update gate, new memory, very similar to LSTM but simpler. We have, for example, ZT, but here we have 1 minus ZT, and this we'll see them. Okay, let's see. By the way, one big difference is what? Can you tell me? Compare this with the LSTM cell. One big difference. So one big difference is the number of gates. It's just 3. Another difference. Can you tell me? No CT. We don't have any CT signal. We only have HT. Now hidden states have been reduced, right? Interesting. Okay. So the reset gate. One of the gates in GRU cell is the reset gate. This gate takes the input at current time xt and also the previous ht minus 1, the previous state, and outputs rt, very similar to what we had before, no peephole, right? And we have wr, ur, and br as the learnable weights. As I said, these are just fully, you can see them as fully connected layers for transforming ht minus 1 to the next thing, okay? Then the reset gate considers the effect of the input and the previous hidden state, of course, xt and ht minus 1, and it controls the amount of forgetting or resetting the previous information with respect to the new coming information. You might be wondering, why do we call them reset rather than forget? Because they had to rename the gates in order to be accepted, right? Otherwise, it would say it's just LSTM. So they renamed that. So reset gate. And also, what does it do? It takes the effect of input and the previous hidden state, and it controls how much I should forget or reset. Comparing equations 74 and 42. Okay, what does it do? It says that shows that reset gate in the GRU cell is very similar to the 4-gate gate in the LSTM cell. Okay, here it is reset gate. Okay, reset gate. This is the reset gate. Now, update gate. What does it do? Another one. So it is update. What does it do? It takes xt at the current time slot, ht minus 1, the previous state, and it outputs zt. So we have again sigmoid activation function, very similar again, but however, wz, uz, and bz are the new learnable parameters. Okay. So again, it takes the effect of input and previous hidden state, and it controls the amount of using the new input data for updating the cell by the common information of sequence. So it considers how much I should use xt in order to update, right? Update. So the opposite of forget, kind of. Comparing equations 36 and 43 shows that the update gate in GRU is very similar to input gate in LSTM cell. Again, they renamed it, okay? However, the big difference of LSTM cell and GRU cell is this. So the renaming was just psychological, but now we go to the big difference. What was that? So this is this. So we have new memory cell. So it takes xt, it takes ht minus 1, and it outputs ht tilde, a p-dimensional vector. Again, it has hyperbolic tangent inspired by what we had in LSTM. However, there's some differences we'll see. So here we have RT, HT minus 1, so Hadamard product between them, times some learnable WC. We have also UCXT, where UC is also learnable, and BC for bias, right? So one difference is this, and another difference is in the next slide. So we have WC, UC, BC for learnable weights. It takes the effect of input XT and the previous hidden state HT minus 1 to represent the new information of current input. And if you compare this equation with equation 32, it says that new memory cell in GRU is very similar to new memory cell in LSTM, although it's a bit different. Note that in LSTM cell, the hidden state, which was equation 34, and the new memory cell, equation 32, were different. That's one important difference. We'll go and dig into that. So let's go back and see equations 32 and equation 34. (32, 34). So this was 32. We had CT tilde, right? And 34, we have CT. They have been kind of combined into one thing for GRU cell. They were different things. Now we have one thing there. So we have CT tilde and we have CT. So as you see, we have CT tilde and CT, but now we don't have like that. In GRU, it has been simplified. So where was that? Yeah. So as you see, we have HT tilde. We don't have any CT here. It has been dropped. We named this HT tilde. In the previous LSTM, they called it CT tilde, but this is HT tilde is very similar to CT tilde. However, we don't have any CT anymore. And also here is a bit different from what we had in LSTM. This is called final memory or hidden state. And what does it do? It takes the outputs of the update gate ZT and new memory cell HT tilde, and we calculate the final memory or hidden state HT, which is a p-dimensional vector. It is a Hadamard product between 1 minus ZT and HT minus 1. Also, Hadamard product between ZT and HT tilde. By the way, this one is a vector of ones, right? Okay. HT minus 1 is the hidden state of the previous time step. Take a look at this figure. Let's see what it is saying. So we have y minus z here. This is z. This is 1 minus z times HT minus 1. This gives us the first term. Now the second term, ZT times HT tilde times this. This is the second term. We add them. It gives us HT, right? Okay. So we had this. Let's analyze it. So what does it do? It has the effect of update gate, previous memory, and the new memory. It aggregates them, similar to what we had in LSTM. In the first term, what does it do? The update gate ZT controls how much of the previous state HT minus 1 should be used based on the input data. Right? Do you know why? Why do we use 1 minus ZT rather than ZT? Recall that ZT is between, where was ZT? Where was ZT? ZT is output of sigmoid. So it's between 0 and 1, right? 1 minus ZT is kind of the opposite effect of ZT, right? ZT was called update gate, okay? Therefore, 1 minus ZT can be seen as 4 gates, right? We want to see the more 1 minus ZT, the more I should use the previous data. Because the more ZT, the more update I have, right? The less I should use HT minus 1. This is the reason I'm using 1 minus ZT, okay? So that's the reason. And now the second term, ZT times HT tilde. What does it do? It controls how much of the new input information should be used. Because HT tilde has the effect of HT minus 1 and ZT. ZT also has the effect of updates. See? I think now it's obvious. So if you multiply these terms together, it's kind of an aggregation of control, how much I'm using the new information compared to the previous information. Okay. And you should note that what? One important thing, HT tilde, it used hyperbolic tangent. Yeah. Why? There is reason for everything here. It's using hyperbolic tangent. Why? Because it wants it to be between minus 1 and 1. So it has its effect in this way. It wants this because ZT is between 0 and 1. HT tilde is between -1 and 1. So it's their product becomes between -1 and 1. So it want to see it might have the negative effect also. That's the reason. It wants to sometimes it might become negative. Also, it's a trade-off of usage of old versus new information in the sequence. The weights are used in backpropagation to pass or block input or previous information based on the input sequence and the time step in the sequence. The final memory in GRU cell is similar to final memory in LSTM cell. However, they have somewhat different functionality. Okay. Now the second variant of GRU. What is that? It's minimal gated unit rather than full gated unit. So it uses the same line of thought. It says, let's simplify further. Okay. So minimal gated unit 41 is another variant of GRU, which has simplified the GRU itself. What does it do? It by merging the reset and update gates into a forget gate. Okay. It says, do you know what is the philosophy behind that? Because the forget is opposite of update. So the more forget I have, the less update I should have. So I can merge them to one thing. Why do I need two things? They're opposite, they're related to each other. Okay. The forget gate, what does it do? It takes the input at current time step xt and the previous the state in the previous time step ht-1, it outputs rt. Okay. Sorry, ft. I apologize. This must be ft. Okay. Then these are the weights, learnable weights. Okay. The forget gate, what does it do? It considers the effect of input and previous hidden state. It controls the amount of forgetting the previous information with respect to the new coming information. Ideas are very repeated a lot. Therefore, it controls both forgetting or using the previous memory and using the new coming information. So the new memory cell and the final memory in the minimal gated unit are these. Because we have merged the reset gate and update gate, and we have forget gate now, the equations are changed. What do they do? So we have in minimal gate, HT tilde becomes this. Now we have, sorry, these were in full gated unit in GRU. These are in minimal unit. As you see, this has been changed to this. So we had RT, now we have FT here. Also, this has changed to this. What do I mean? So we had ZT, we have FT now here. We had ZT, we had FT here, right? So the equations have changed. Bidirectional RNN and LSTM. So what does it do? It says that a bidirectional RNN or LSTM. So by the way, GRU is over. Now we go to the next section, which is bidirectional RNN and LSTM. It processes the sequence in both directions, left to right and right to left. Okay. In the first glance, online causal tasks such as reading a text or listening to a speech do not have access to the future. It has a paradox with causality, right? However, so it seems that they violate causality. However, in many of these tasks, it is possible to wait for the completion of a part of a sequence, such as sentence and then decide about it. What do I mean? For example, in a speech recognition, I can wait for a sentence to be completed. And then I have the whole sequence. I can process it in both directions. Or in text, I already have the text if it is not being generated, right? If it is being generated, I can wait for a sentence to be completed and then process it, right? For example, yeah, as I said, okay. Then also, why do we need bidirectional process? What's the philosophy? Consider this sentence. The police is chasing the thief. If you look at it left to right, you first see police and then thief, which are related to each other. If you go right to left, you first see thief and then police. They're also related to each other, right? So you see these related words in both directions. Which one do you see first? That's important. Okay. Bidirectional RNN So we have both bidirectional RNN and bidirectional LSTM. Bidirectional RNN was first proposed in 1997, reference 20, and further exploited in 1999, reference 21. What does it do? It uses two sets of states, each for one of the directions. Okay. So previously in RNN, we had one state, HT, or right, we had HT, right? Now we have two sets, HT to the right, arrow to the right, HT to arrow to the left. So we have two variables now, two sets of variables, each of which is a vector. Okay. So as you see, this we already had it in regular RNN. However, we are adding this. So in both directions. So this goes from left to right in the sequence. This goes from right to left. Okay. And YT now, do you remember? YT was VHT only in RNN plus BY. Now we have VHT for the left to right plus VHT from right to left. And these have two different weights. V left to right, V right to left. Okay. If we unfold it, you remember we had unfold of RNN, it will be like this. So only previous in regular RNN, we had these only and the outputs. Okay. Now in bidirectional RNN, we also have this right to left. And the output takes both the HT in the left to right and right to left. It takes both of them. So we have this arrow and this connection, both connections, right? And as you see, notice the direction of processing. Left to right and right to left. Okay. By the way, for each of these, then we use backpropagation through time, similarly as was talked about before. And it is noteworthy that the deep variant of bidirectional RNN is, you can see it in reference 42. Okay. Then bidirectional LSTM. It was first proposed in 2005. References 18 and 19. As obvious from its name, it is two LSTM networks, each of which processes the sequence from one direction. We have one LSTM from here, from left to right. We have one LSTM from right to left, and we feed XT to each of the cells. And however, the output at time t, it takes the output of LSTM from left to right at time t, and the output of LSTM from right to left at time t, right? By some matrices V. V left to right and V right to left. So basically, they're adding more parameters. They're doubling the parameters, but they are processing the sequence from two directions, right? There are two LSTM networks which are fed with the sequence in opposite orders. Experiments have shown that bidirectional LSTM outperforms the unidirectional LSTM. I think it's obvious because we have more parameters to learn. We also process the sequence in two directions. We have more information. Okay, now the next thing is ELMo. ELMo is was one of the very important language models in NLP before attention mechanism. Several years ago, it was one of the state of the art. So what does it do? ELMo is short for embeddings from language model. ELMo network was first proposed in 2018. Very new. Okay, so it's a language model which makes use of bidirectional LSTM networks. Okay, so it is one of the successful context-aware language modeling networks. What do I mean by context-aware? This is an important thing in NLP. So we have several techniques in NLP. Even before these things, after RNN and LSTM, there were at least two methods which were very important and state of the art for several years in NLP. One of them was GLOVE. One of them was word-to-vec. I don't know if you have heard of these or not, but these are not deep networks. I think word-to-vec is only one layer or two layers of neural network. Shockingly, it works very well. Okay. Nowadays, in new NLP methods, the input of those NLP methods, such as BERT and GPT, the input of them is word-to-vec embeddings. So first they take the words, they feed it to word-to-vec, they find the word-to-vec embeddings, and then they feed it the word-to-vec embeddings to the BERT and GPT. Do you get it? So that's one important thing. But word-to-vec, I think by its name, I think it's obvious. It means that you take a word and you convert it to a vector. So they are learning some vector embeddings for the words, okay? They were not context aware. So they were not really looking at the other words in the sentence for finding the embedding, What do I mean? For example, the word bank. It has only one word, one embedding in word-to-vec. However, bank might have different meanings. One of them is money in the bank. Money is in the bank. The other one is there are a lot of vegetation in the bank of river. Two different, completely different words. The same word, but two different meanings. However, they have one word-to-vec embedding. Of course, context-aware embeddings are better, right? So that's one thing. Again, the idea of analytical philosophy. What did the principle of context by Frege a century ago? Okay, so ELMo was context aware. What does it say? It contains L layers of bidirectional LSTM networks, where the output of each bidirectional LSTM is fed to the next bidirectional LSTM. So this is, do you remember? So we had LSTM, bidirectional LSTM had two sets of LSTM, two LSTM networks in two different directions. Now ELMo is a stack of them. It's a stack of bidirectional. So layer one is one bidirectional LSTM. Layer two is one bidirectional LSTM. As you see, they are making it more complicated, more and more complicated. So the more parameters they have, and of course, nowadays we have a lot of data. Why? Why do we have a lot of data? We have the whole internet. We have the whole internet data, text, okay? They use that in order to train the networks. Therefore, they have a lot. They know that they don't get overfitted. So they increase the parameters. And they have servers also. They have time, so let's train. And then, so we have bidirectional, and we concatenate this HT and this from the two LSTM directions. This gives us the hidden states between the layers, and we feed the hidden states of the previous layer to the next layer. And then we add the outputs of the bidirectional LSTMs together in order to have the aggregated output of the network, ELMo network, okay? So in the bidirectional LSTM networks of ELMo, we have V equals I. What do I mean? YT equals HT. They don't have any YT, okay? The output is the state itself. And what at time slot T and layer L, the outputs is like this. So they concatenate the hidden states as shown in this figure also. They concatenate them. Then a linear combination of these hidden states of layers is considered to be the embedding vector of ELMo. As I said, we have a linear combinations of the outputs, or outputs are equal to hidden states here. And here it is. These gamma and SL, we have L of them, right? These are the hyperparameter scalar weights, which can be determined for a specific task. It depends on our task. What is it? So we have various tasks in NLP. One of them is question answering. What do I mean? You give me a question sentence, I answer it for you. Another thing is translation. You give me a sentence in English, I make it French, something like that, in natural language processing. Okay, so you determine gamma and SL for your own task. Acknowledgement. This slide deck is based on our tutorial paper, Recurrent Neural Networks and Long Short-Term Memory Networks Tutorial and Survey. You can take a look at that. And some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. And these are the references. Let's go see them very fast. I don't go through them because we don't have enough time. Okay, so let's have a break and come back at 8:45. Thank you. Okay, so now we continue with attention mechanism, transformers, BERT, and GPT. So this slide deck is the state of the art for natural language processing. Okay, so NLP started with what? Recurrent neural networks, then LSTM, then Word2Vec, which we didn't cover, then GLOV, then ELMo, then attention mechanism, transformers, BERT, and GPT. Okay. So first, let's talk about attention mechanism. When we take a look at the scene, okay, do we attend to all the regions of the scene equally? In other words, for example, when you are looking at Mona Lisa portrait, right? Do you see everything equally? Which parts of this image do you attend more? Her face, her lips, her smile, her eyes, right? Do you notice that there is a river behind her? Or there is something? No, not much at the first glance, right? So you attend to her face more. So you attend to some pixels or some regions of the image more than the other parts. That's one. When you read, especially when you're reading fast, okay? One of the techniques for fast reading is what? Skimming in a way that you attend to more important words. You don't read all of the words, right? So for example, Mona Lisa is a portrait painted by Leonardo da Vinci. So Mona Lisa, portrait, Leonardo da Vinci. These are important. Is a boy maybe painted? These are not that much important, okay? So for fast reading, you just attend to some words more, okay? In other words, either it is in natural language processing text or it is image. When you are attending to some parts more, it means that you're just waiting. You're waiting the pixel, you're waiting the words. Some words will have more weights than the other words. Some pixels will have more weights than the other pixels. So this is called attention, right? You are having attention, and attention is nothing but waiting. So in order to model attention mathematically, you use waiting. Okay. Also consider an autoencoder. So you have an encoder, you have a decoder, okay? Assume, so an encoder takes something, encodes it into something, and then decodes that and tries to, for example, to reconstruct it, okay? If we reconstruct it, it's called reconstruction autoencoding. If we denoise it, it's called denoising autoencoding. If we generate something, some new things by the decoder, that's called generative or inferential autoencoders, such as variational autoencoder or adversarial autoencoder. We will cover these, okay? So we have various types of autoencoder. Consider one autoencoder which has encoder, decoder. It takes some input and then it gives me something in the latent space. So this is called latent space, right? And this latent space captures the concept. For example, I give the elephant, the cartoon elephant to the encoder. It embeds it into some latent space, and the decoder gets that and outputs a real elephant, okay? In this case, in the latent space, I have the concept of elephant, the concept of it. This is exactly what happens in our minds. When we talk about elephant, when I tell you elephant, do you have a specific elephant? Am I talking about a specific element? No, I'm talking about the concept of elephant. Again, it becomes a bit philosophical, right? The concept of elephant. So this, by the way, is also called context vector. So we embed that into a context vector, which encapsulates the concept, okay? And as you see, we can use autoencoder for domain transformation, domain adaptation, and domain generalization. So by domain transformation, I mean like this. Cartoon elephant gives you a real elephant. Domain generalization and adaptation, there's a difference between them. What is the difference between domain adaptation and generalization? As far as I remember, in domain adaptation, we learn various domains in order to be able to handle various domains. So in training phase, we learn all of the domains that we can. Then in the test phase, whatever domain comes, we can adapt to that. We can handle it. In domain generalization, we learn some domains. However, in the test phase, we might have a new domain. However, we learn it in a way that it can handle an unseen domain which wasn't used in training. So domain generalization is a bit harder than domain adaptation. Okay, that's fine. Okay, now consider, so as I said, the context vector we have in the latent space in the middle, denoted by C, is a p-dimensional hidden, in the p-dimensional hidden space or latent space. Then consider that we want to have an autoencoder which transforms a sequence to another related sequence. For example, it gets a sentence in English and translates it to French, right? So this is called a sequence to sequence model. Why? Because it takes a sequence, it outputs a sequence, but these sequences are related to each other. A sequence to sequence model, okay? Suppose the number of words in a document is n. We have n words. Let the ordered input tokens or words, by the way, in NLP, you can see they also call the words tokens, doesn't matter. The input tokens or words of the sequence denoted by this, x1 until xn, okay? Then the output sequence will also be y1 to yn, okay? See this figure, what do we have? Here, every hidden state is fed to the next hidden state. So by the weight matrix W. This is exactly what we had in RNN, right? Do you remember? And if we see it in an autoencoder model for sequence as a sequence to sequence model, the last hidden state of the encoder gives me the context vector. Do you agree? The last hidden state is the of the encoder is the context vector. Then the context vector is fed to the decoder, and we have it like this again in order to generate the outputs. So you can see the probability of yi given the previous y's. Yi is the output of the ith time slot. Given the previous ones is a function g of the previous yi1, the li, what is li? The hidden state in the decoder, and the context vector c, right? So we get, for example, for yi, I get li, and also I depend on yi minus 1 and c. In the sequence to sequence model, every word xi produces a hidden state hi. So xi gives me hi. And as I said, so hi is fed, it becomes hy plus 1 through the matrix W by projection after matrix W. And you can see matrix W as a layer, linear layer, right? By weights W. And we have only one context vector here. And that context vector equals hn, the last hidden state of the encoder. This is exactly what we have in sequential models such as RNN and LSTM, right? If we use RNN for autoencoder, it becomes like this. However, assume we have a sequence to sequence model now, this time with attention. With attention. What happens? So here we have similar to before. However, the difference is that C became CI. What do I mean? I have now n context vectors, not just one context vector. Okay. And Ci, you can see it, the ith context vector is a linear combination of all of the hidden states in the encoder. So do you see this? Linear combination of all of the hidden states. Rather than having one context vector, which is equal to the last hidden state of encoder, we have n context vectors, each of which is a linear combination of all of the hidden states in the encoder. And I think it's obvious for you why it is called attention, because it's a linear combination with some weights, Aij. I said attention. If you model it mathematically, it's just weighting. And we are weighting the hidden states, right? So in other words, we say which words in the sequence have more effect on that word, on the other word, okay? Or it determines which words this specific word attends to more. This specific ith word, right? Attends to more. And this is called attention. Okay. So compare this figure with this, and you'll see the difference. Okay. The original idea of arithmetic linear combination of vectors was what? In word-to-vec method. So in word-to-vec method, in order to sell their method, they said this. So let me add a page here. Word2Vec learns some embedding vectors for the words in natural language processing. It's not a deep network. It's a shallow network with 1 or 2 layers, as far as I remember. It uses logistic functions, and it uses simple optimization, okay? So it learns some embedding vectors, but for them to sell it, they were very wise, the authors. So they learned some embedding vectors. Then they found out, okay, let me take the vector for king. Yes. Yes. Then they said, okay, I also consider the vector which I learned for man. Also consider the word which I learned for woman. Also consider the word which I learned for queen. So there are some vectors for each of these with the same dimensionality, right? So they said king, let's have king minus n, man, the vector of man, plus the vector of woman. They interestingly saw that it is almost equal to the vector for queen. However, a weak version of this was also satisfied for PCA. If you apply PCA, if you learn PCA, any dimensionality reduction method, any embedding vector, any method for finding embedding, if you apply on these, almost you get this. However, they were more accurate, okay? But up to that year, no one was showing the embedding like this. So this was their wise idea in order to sell their paper, okay? And it even was advertised in magazines. Oh, by the way, we learned an embedding which could learn this, okay? So as I said, we have arithmetic between words here. Later, papers came for arithmetic between images. They learned, for example, within variational inference or in GAN, generated adversarial network, which we will cover, they learned something like this. In the latent space, they considered the point which was corresponding to a man, for example, with glasses. They also found the point which was corresponding to 2 glasses. No, sorry. Yeah, I think 2 glasses. Then they subtracted this. It was almost equal to the point corresponding to that man without glasses. So this is a point in the latent space. If you pass it through the decoder, it gives you this matrix, this image. This is also another point in the latent space. Then this is also another point. So what did they do? First, they got this point, pass it through the decoder, it gave this image 1. Then this point, pass it through the decoder, gave image 2. They subtracted these 2 latent vectors. They pass it to the decoder. It gave image 3. And interestingly, it has semantically learned. So it means that the latent space which I learned is semantic, right? So we had at those years, it was very interesting to find arithmetics between words, between images, and between these things. Okay. Now the idea is very similar. We have arithmetic linear combination here. Okay. And the sequence-to-sequence model with attention considers a notion of similarity between the latent vector Li-1 of the decoder and the hidden vector Hj of the decoder. So we have Li-1 and Hj, another. So Hi or Hj, doesn't matter. I'm denoting Hj because I don't want it to be confused with Li-. So what does it say? This is a similarity between the hidden states in the decoder and encoder. Basically, I denote it by Sij. Basically, it means that what is the relation of the jth output and the, ith output and the jth input, right? For example, do you know French? I don't know French. Do any of you know French? No. Okay, I know 2 languages, so I use them. I know English and Persian. So, for example, the sentence "I am a student," okay, its Persian sentence is "Man yek danish amuz hastam." Okay, then if you see the similarity, so student in Persian is danish amuz. Okay, so if you see the similarity between the word student and danish amuz, it picks. Okay, however, if you man is I in English. Okay, so if you see man, similarity of man and student, it doesn't pick. It's smaller, right? So you can see the similarity of output words with the input words. You have a lot of similarities, all of the permutations, right? Okay. Intuition. The output word yi depends on the previous latent vector Li-1 and the hidden vector Hj. Also, yi depends on Li1 and the hidden vector Hj depends on the word xj. Therefore, you can see Sij as the impact of the input xj on the output yi. Okay, therefore, score Sij shows the impact of the jth word to generate the ith word. Did you get it? Okay. So again, we are seeing it as similarity. Okay. Similarity is used in attention also. We'll see. I think it's obvious for you. Why? Why is similarity? When I say, if does a word attend to another word, I can model it by similarity. How similar these 2 words are to each other. If they're similar, so they need to attend to each other, right? To make this score a probability, this score is not necessarily a probability. In order to make it, the technique was what? You tell me. Softmax, one of the techniques we already talked about is softmax. So we use it in softmax. E to the Sij over summation of e to the Sij. So it's have a Gaussian distribution, right? The score vector, this score vector behaves as a discrete probability distribution now. Okay, it sums to 1 and they are between 0 and 1. Therefore, in equation 3, so Ci, do you remember? We had Ci, the context vector, was a linear combination of the hidden states in the encoder. What does it do? The weights in this, what are the weights in this linear combination? Aij. And Aij, we just made it probability. So the weights sum to 1. And the weights with higher values attend more to that corresponding hidden vectors, right? Okay, consider this sentence, for example. So we can see the relation of words, how much we have attention. For example, the FBI is chasing a criminal on the run. Then if we are at the word there, it's just there. Then we go to FBI. FBI is just FBI. There is not that much important. Then we go to is actually should attend to FBI because who is FBI is. Then chasing is more related to FBI than to is. Therefore, its attention score is small. Then we go to it's not that an important word. Then we go to criminal. Criminal actually is important for both chasing and FBI. We go to on is attendant to ease, doesn't matter here. Then we go to we go to run. Run is attendant to chasing and criminal. So I think you know what I'm talking about. The words relate to each other. Okay. And for understanding how the words relate to each other, we need a composite embedding. As I said, word2vec and glove, they are not really context-aware embeddings. What do I mean by composite embedding? It means that I care about the context, okay? And attention actually cares about the context because it takes into account the attention of the words with each other. Okay, now consider, do you know database? Have you passed any course on databases? If you have, you know that it's related to, so when you have a database, it has keys and values. In Python, for example, you can see it as a dictionary, and they are usually modeled as hash tables, okay? So in Python, it's implemented as dictionary. So we have some keys, we have some values, we have some query. And for query, we see which key matches to that query, and we output the value corresponding to that key. Okay, this is what a database is doing. And they have improved its time complexity, so it doesn't need to go and search row by row, okay? Then, this is a hard definition of database. We can have a soft definition of database. What does it mean? Rather than outputting only one of the rows, one of the values, so only we match in hard definition, we match with one of the keys and we output one of the values. In soft definition, we see how similar the query is to each of the keys. And using that similarity, we use the same similarity scores in order to have a linear combination of the values. So for example, I see how much query is similar to key one. Then the value, the output value, for example, it gives me Sij. No, sorry, Aij. I use the same weights here. Okay, so it gives me A, for example, A1. This gives me A2, A3, and then I use, so value, the value will be A1 value 1 plus A2 value 2 plus until the end, right? So I calculate the similarity of the queries with the values, and I use the same similarity scores for linear combination of values. Therefore, the value in soft definition of database, the value is a linear combination of all of the values, where some of the weights might be 0, right? So, as I said, similarity of the query with all of the keys, and then we use this in order to have a linear combination of the values. And we can call it attention. This is query, Q, the vector Q for the query. And we have N keys, KIs, N values, VIs, right? SI is what was the AI? It was the softmax of SI. Do you remember? We talked about it. Softmax of SI. And what is SI? It's a similarity. Any similarity measure between query and the KI, the query and the key, right? So SI is a similarity of query and the I key. Okay. So you can plot it in this way. So we have, for example, in this figure, we have 4 keys. We calculate the similarity of query with each of these keys in order to give us S1 to S4. Then we have softmax, and each softmax uses all of the values. Therefore, we have a kind of a fully connected thing. In order to calculate A1 to A4, why am I having a fully connected? Because in the denominator, I'm using all of them in the denominator of softmax. And then I add them by the values in order to have the linear combination of the values. It gives me the attention, right? As you saw, I'm modeling attention mathematically. Then the similarity SI can be any notion of similarity. Do you remember here? We said that SI is similarity of query and the key. So what is the similarity? It can be any function or any notion of similarity. Some of them are inner product, right? Inner product. Inner product of two vectors shows how similar they are. SI, you can see the Q transpose KI. Or you can have a scaled inner product where you scale it by square root of P, and P, I think, was the dimensionality of Q and query and key, because they are vectors, right? You can also have general inner products. So we have Q transpose WKI, where W is a learnable weights learned by backpropagation. You can also have these additive similarity. So WQ transpose Q and plus WK transpose KI. And these are learnable vectors by backpropagation. Why? Why does this make sense? Because assume the two vectors are similar. So they're almost in the same direction. If you add them, they will be added a lot. They will amplify each other. If they are very different from each other, then they will kind of subtract it, right? Also, another similarity measure is kernel. So you can see, so this is linear kernel, right? Kernel matrix. Okay, so this is equation 6 that we talked about attention. What does it do? Calculates the attention of a target word or a query with respect to every other input word or keys. Now, use the idea of attention or soft database for natural language processing. What does it mean? So every word that I'm processing, I can see it as a query, and every other word as key. Okay? So you see how similar this specific word is to other words. How much attention we have between them. How similar the other words of the sequence are to that word. In other words, we see how impactful other words are for this word. Consider this example. I am a student. We are processing the word student. So query is a student. Values are I, am, and a. So assume I calculate the similarity, and the similarities become like this. Between I and a student is 0.7. Between am and a student is 0.2. Between a and student is 0.1. They sum to 1. Okay. Then you can write the attention for the student as 0.7 VI, the value, the embedding of I, the 0.2 plus 0.2 value of am plus 0.1 value of a, something like this. By the way, I'm building gradually. You'll see that how we are going to use them in deep neural network. Okay. Let the words of a sequence be d-dimensional in b-dimensional space. How? Word is just some letters. How can we consider the words to be xi vectors from n vectors, each of which is d-dimensional? How? Can you tell me? Suggestions? These are word-to-vec embeddings. I told you, word-to-vec or GLAV, what do they do? So word-to-vec has learned something. It's just like a dictionary. You open that dictionary, you see, I want the embedding for the word student. You go to this dictionary, you see, okay, oh, by the way, student, its vector is usually, I think, a 200 something dimensional vector. Every word is a 200 dimensional vector. You take it, you use that, right? It's exactly like a dictionary. They have learned it and they have put it in a dictionary. So you take that, okay. This d-dimensional representation of words can be taken from any word-to-vec embedding, such as word-to-vec or GLAV. Then the query, key, and value are projection of the words into p-dimensional and r-dimensional subspaces. So for query and key, they are p-dimensional both. Why? They must be from the same dimension because I'm using their similarity. How can you compare two different vectors which are not the same dimensional? Okay, they must be. And what is P here for query and key? Is the dimensionality of word-to-vec, 200 something, right? However, the dimensionality of value is our choice. We are learning them, okay? And we denote it by R, okay? So value is the R dimension. By the way, sorry about that. I said P is the dimensionality of word to vec. I was wrong. So Xi is the dimensional, the dimensionality of word to vec, okay? I project it with some linear layers, WKW, WQ, WK, WV to some other space. So for query, I project d-dimensional word-to-vec embedding onto a p-dimensional space. For key, I project d-dimensional xi to p-dimensional space, and for v, I project it to an r-dimensional space. But I know that the dimensionality of query and key should match because I'm gonna compare their similarity, right? So far clear? So D, dimensionality of word-to-vec, P, dimensionality of Q, query and key, R, dimensionality of value. And these are W, Q, W, K, W, V, learnable weights by backpropagation. Okay, now let's put them. So I have X's, put them column-wise next to each other, D by N, X. Then also I have queries, keys, and values, okay? So I put them next to each other in order to have these matrices. Okay. By the way, why am I using these W's? Because I don't want to use the embedding word-to-vec embeddings directly. I want to have a transformation of them. That's it. Okay. Because maybe after a transformation, they get better. They get better. And I'm going to learn them by backpropagation. Okay. And as I have said that Q transpose Ki, you can see it as also a kernel, because kernel matrix also measures the similarity. Okay, now do you remember attention, which we talked about? What was that? Equations 7 and 8. If I can, let me. Give me a sec. Equations 7 and 8 are here. Let me repeat them to you. Okay, so equation 7 was this. SI equals similarity of Q, query, and KI. Equation 8 was AI was softmax of SI. Do you remember? Okay, now let them be in the matrix format. So what do we have? Here, we could say that, by the way, do you remember one of the similarity measures was scaled inner product? So we had Q transpose Ki over square root of P. If in matrix format, it is this, right? And then I put this SI inside the softmax. Also, I put it inside the softmax. However, do you remember what was equation 6? Equation 6 was this. Attention was summation of linear combination of the values, AI, VI. Do you remember? Now I have, what is this, by the way? So this AI this is a AI, right? This is AI times VI. Where did this summation go? Because I'm writing it in a matrix format. Multiplication in matrix sums them, right? So the summation was absorbed in the matrix multiplication. And this gives me equation 16 in matrix format. Okay. Now consider that I calculate this between the words of the same sequence. So I have one sentence, I am a student. I calculate the attention of every word in this sentence with every other words. This is called self-attention. Why? Because I'm calculating the attention of my words with myself. Now, if I have two sentences, I am a student and he is Jack, whatever. You can have the words of this sentence and the words of this sentence and calculate the similarities of them. Or this might be a sentence in English and that might be a sentence in Persian or French. We can calculate the similarities between the words. That is called cross-attention, right? So self-attention, cross-attention. We can have attention. I will go deeper into that. So I'm building up. We can have attention in other fields such as vision, machine vision, computer vision, and speech recognition. So speech, I think it's obvious. You have some phonemes, units of speech, and you can see their similarities. For example, similarity of E and B is high. E and U, they're different, right? They're different. So also, so in vision, you have this. For example, you have an image, you have a convolutional neural network. It gives you some feature vectors, right? And then you can feed these feature vectors into some LSTM. This you can see it as encoder as a CNN and decoder as an RNN or LSTM. This is without attention, okay? Without attention. Then using this, what can I do with this left-hand side? This is an autoencoder. We already talked about it in the first slides. This encoder gives me a concept vector. This is giving, so it's for domain transformation. What am I doing? So I'm transforming the domain of image into text. It is caption generation for image. It gives me a sentence for describing, for example, an elephant is in water, something like that, right? However, I can have attention in it. In the decoder, I can also calculate the attention of the words with each other. Also in encoder, I can calculate the attention of the patches of pixels with each other. So I can have attention for NLP, also attention for images. Consider these patches. I can have patches of the image either with overlap or without overlap. And the patches also, we can calculate the similarities of the patches with each other, right? So you can see image as a sequence of pixels. Interesting, right? Attention in other fields such as vision, they are also called in any field. It's called their papers, the titles of their papers. Attend, tell, and do something. For example, for caption generation of images, it's called show, attend, and tell. See the references, you will see. Caption generation for images with ownership protection. Protect, show, attend, and tell. Text reading from images containing a text. Show, attend, and read. Translation of one image to another related image. Show, attend, and translate. Visual question answering. Show, ask, attend, and answer. Human-robot social interaction. Show, attend, and interact. And speech recognition. Listen, attend, and spell. These are all papers with similar titles, okay? Now transformer. So far we talked about attention. Now transformers. Attention is used in transformer, okay? So as I said, we have autoencoder, which takes some input, gives me some concept, and then outputs something, right? Do you remember autoencoder? So in other words, it transforms the input to a related output. Okay. An example is translating image to some caption. An autoencoder, therefore, it can be said to be transformer because it transforms input to output. Right. Guys, this is important. We'll go into an interesting part. So why can I call autoencoder transformer? Because it transforms. So hence the name transformer, okay? But transformer does use attention. So this is a transformer, which is an autoencoder. Of course, it has encoder, decoder, because it transforms. And in the middle, we have a concept of the words. For example, encoder inputs can get English words, outputs can give me French words or related words, right? Okay. And we have encoder and decoder. Let's talk about each of them. Encoder of transformer. So encoder, what does it do? It takes the input sequence, inputs here, of n words. So D is D-dimensional, each of which is D-dimensional. And D-dimensional is, you tell me, word-to-vec embeddings, right? And then it maps them into context vectors with attention mechanism. We will see how the details. Okay. And there is no recurrence here. We'll see in transform that the transformer doesn't have any recurrence. We can't unfold it like we did. Therefore, there was a paper which came, the paper which proposed transformer. What was it called? Attention is all you need. It means that you don't need recurrence anymore. Attention is all you need. It was a breakthrough in natural language processing. Until then, people used to use LSTM and RNN a lot. But after that, they were completely out of date. Nowadays, people are using transformers, okay? So what does it do? It takes the input, then input embeddings. What is this input embedding? These are the word-to-vec, for example, embeddings, right? Then it adds a positional encoding. Why? There's a reason. As I said, when I don't have any notion of recurrence, I get lost in the information of order is lost. I need the information of order. Why? Because, do you remember the data sets which are not sequential? For example, toy data sets, image data sets, toy data sets, whatever you have. Okay. Does the order matter for them? Whether this is the 0.1, then 0.2. Actually, we shuffle them. The order doesn't matter. Do you remember in convolutional neural networks? If in a data set which is not sequential, you consider the order, it's a flaw. Why do we shuffle? Because we want to be robust to the order. The other way around. In a sequential data, however, if you ignore the order, that is a flaw. You have to take into account the order. Okay? Therefore, in order to take into account the order, we need to have the information of order. But how? We add the positional encoding, which encapsulates the information of order in a way that I will tell you. So I define a position vector Pi. It's a bold Pi. Don't confuse it with a not bold P, which was a dimensionality of query and key. That was different. This is bold Pi. This is a position vector for the ith input, xi. Okay. So xi is d-dimensional. I let Pi also be d-dimensional. Why? Because I want to add them at the end. Okay. Here, do you recall this add? Okay, I want to add them. Therefore, they need to be from the same dimension. Then I define Pi to be like this. So I have, it is a vector, right? I have odd elements and even elements. Do you agree? Odd elements and even elements. So if for odd elements, I use this. For even elements, I use this formula. So this is cosine, and by the way, what is I? What is j? J is between 0 and d over 2. Why? I have d elements, d over 2 of them are odd, d over 2 of them are even, right? So, sorry. So d over 2 of them are odd, d over 2 of them are even. Therefore, j goes from 0 to d over 2. And then what happens? So 2j plus 1 are the odd elements. 2j are the even elements. I think it's obvious. Then what happens? This is cosine. So I, what is I? I is the ith point, the index of the point, and Pi. So we have P1, P2, P3. Why? Because each word in the sequence, I want to have a position vector for them, right? A position vector for the first word, a position vector for the second word. So I denotes the index of the word in the sequence, and J, as I said, for the odd and even elements. And if you use this, so you have a vector, you fill it out with this formula. It has just a formula, cosine and sine, right? If you fill it out, it will become something like this figure. I'm plotting them here. So what is this? This is I. This axis is I. This axis is the elements. There. So this axis what do I do with my device? I don't know. Yes. So this axis is I, okay? And what is this axis? This is the elements of Pi. So this means this is P1. The second row is P2. Do you agree? Did you understand what I'm saying? That and each of these is a P vector. Each row is a P vector. The first row is P1. The second row is P2. The third row is P3. Right? So what do I mean? This row is a position vector for first word. This row is a position vector for the second word. And I'm drawing the position vector for 10 words. Do you see that they are completely different, all of them? They're different. So they're encapsulating the position. You go forever. They're always different. No matter how length you go onto. And you see that the difference is usually in the first dimensions of position vector. Here, these first dimensions are more different than the last dimension. And this is because of the behavior of sine and cosine. Okay? So we could encapsulate the information of position in the position vectors. Now I add them to the word embeddings. After this add, the information of position is encapsulated in the xi. Right? Now we are here. So we are going up in the encoder. Now we are here. We go, the next thing is multi-head attention. Multi-head attention. What does it do? So what are these three? You tell me. These are query, keys and values. Three things, right? Query, keys and values. And I'm using attention, okay? So attention we already talked about. We have some weights. We already talked about the formulas of attention. However, this is multi-head attention. What does it mean? It simply stacks each of them. So it applies attention. What do I mean by stack? Sorry. Let me tell you in more accurate thing. So I have attention. Then I pass it through another attention. Then I pass it through another. Okay. I do it H times. If I do this, do you know what happens? The first head, what does it do? It attends, it says how much every word attends to every other words. Okay. The first attention determines how much every word attends to every other words. The second repeat says how much every pair of words attends to every other pairs of words. The third repeat, it says how much every pairs of words attends to every other pairs of words, and so on. You see how big and powerful it is becoming, right? The first attention says how much I am attending to you. The second one says how much we two are attending to two other people. The third one, how much pairs are attending. I need to imagine, it's so complicated. Okay, so you do it H times. That's why transformers are working very well. They're calculating the attention of pairs of words with each other. Okay, so we have multi-head attention. And by the way, it's ideal is very similar to maximum mean discrepancy. What is maximum discrepancy? It's simply, if you model it mathematically, it's like this: phi of xi minus phi of xj. I will tell you what it is. Squared out to norm or whatever, some normal phi of xi minus phi of xj. What is phi? This is the pooling function of kernel. Do you know what kernel? If you don't know, take a look at my sessions on kernel SVM in statistical machine learning. So in kernel, you have some pooling functions to the Hilbert space, okay? So you have some mapping from xi to the Hilbert space, reproducing kernel Hilbert space. And then you calculate the distance between these two, okay? And it can be seen as a distance between the kernels, okay? But what does it say? It says basically, assume xi is from some distribution. Assume xj is from another distribution, okay? I want to compare two distributions. The first one thing is that one solution is that you compare their means, right? Another solution for difference of two distributions, you compare their variances. Variance is related to second moment. If you know what moment is, if you don't know, just take a look at that. Search it. First moment, second moment, third moment, okay? First moment is mean. Variance, I think, is related to the first moment and second moment, okay? I already have proved the formula in a statistical machine learning course. So you can go to higher moments. And these moments, you have infinite number of them, okay? So it's doesn't suffice to calculate the difference of first moment and not sufficient to calculate the difference of second moment. You need to calculate the difference of all of the moments. And maximum mean discrepancy, which is this, does that for you. Why? It maps them to the Hilbert space, and in the Hilbert space, if you calculate their difference, it's like that you're calculating the difference of all of the moments in the input space. Okay, this is the idea of maximum mean discrepancy. And now you see the relation of maximum mean discrepancy with multi-head attention. Why? Multi-head attention is they're calculating the differences of the pairs of the word and pairs of the word. You can see it as like calculating the difference of moments of the distribution, right? Ideas are repeated in machine learning. Now, what do we do? So this is what we had. So we have X, we have several W's for each of the heads. So WV1, WV2 to WVH, it gives me V1 to VH values. I have X also, K1 to WKH. Using them, I have K1 to KH. So H keys, H values, H keys, and then H queues. Queries, sorry, H queries, H keys, and H values, okay? And then, so using all of these weights. So this is multi-head attention. I have H of them. Then what do I do? So as I said here, I have H of them. QI, VI, KI, right? Then what do we do? Using a scale dot product similarity that we had in attention, we can calculate Z1 to ZH for each of the heads. Then we concatenate them. We concatenate them, and using a linear projection, WO, a linear layer, WO, I have ZT, Z total. This is what they are doing. So basically, so as I said, we have ZH of them, we concatenate them. Then WO transpose, which is a fully connected layer, it gives me Z total, right? This is the multi-head attention in detail. Then we have layer normalization. So here, we are here now. Can you see this in the figure? We are here. After multi-head attention, before add and norm. I'm now in this slide, I'm talking about add and norm. What is it? Interesting. First, we add. What do we add? The output of, what was the output of multi-head attention? ZT, right? What was the input of multi-head attention? X. So I'm adding the output of multi-head attention and its input. What does it remind you of? Please tell me. Residual learning, ResNet. They have been inspired by ResNet. Okay, add is just ResNet. Then they do this. What is this? You tell me. Please tell me. This is batch normalization. We already talked about it. Do you remember? What does batch normalization do? You subtract the mean and you divide by the standard deviation in order to standardize the data, or Z-score normalization. Do you remember? This is batch normalization. So they have ResNet idea and the idea of batch normalization. So add and norm is this. By the way, the standardization is good for covariate shift. We already talked about it in batch normalization. Then we are here now. We are here, so we are going up, right? Then we have a feed-forward layers. So henceforth, we have ZT prime, which is after add and norm. Then what do? We have the feed-forward neural network. Assume this is the ZT prime, and the output of feed-forward neural network, I again do add and normalization. So this is the idea of resonance. So again, after feed-forward neural network here, I do add and normalization again. The idea of ResNet and batch normalization again. Okay. So now where are we? We are here now. We already talked about everything. However, we didn't talk about one thing in encoder. That is this. What is this n times? What is this n times? We simply stack it n times. So we have n times of this. Why do we do that? We want to have more parameters to learn. Because we have a lot of data, internet data. We have enough data not to overfit. Let's add parameters, learnable parameters, in order to learn nonlinearity of data. Right? Then through experiments, they have found n equals 6 is good. So we have 6 times of this. Do you let me explain decoder and then we'll leave? No? It's fast, I will tell you. So decoder is very similar to encoder. Take a look at that. But what do we do? First off, we take the shifted outputs. So the outputs of the decoder, we shifted one if you are processing left to right, if it is English, okay? We shifted one to the right. Why? Because I'm taking the output again as the input, but I need to shift it. Shift it to the right. Why? Because the next word has been generated. So I can go one to the right. The next word has been generated. Okay? I can shift it. And then I take the output embedding, again by word to word, for example, whatever. Then I have positional encoding. Again, I have PIs, I calculate PIs for these. So I add them in order to have the informational position. Then I'm here, okay? Then I have masked multi-head attention. So everything is similar here, except masked here. In the encoder, we had multi-head attention. This is masked multi-head attention. What does it do? So take a look at, so masked multi-head attention, it masks away the forthcoming words after a word. Because we don't have the future words yet. We are generating them one by one, right? In attention, do you remember, for example, in I am a student. For the word am, you're considering the word I before that, also after that, and student after that. So you're calculating the attention of words before and afterwards. But here in the decoder, in the encoder, the input we already have it. In the decoder, the output, we are using the output, and we don't have the future words yet. Therefore, we have to mask the future words. We have to. Do you get it? In order to only calculate the attention of this word only to its previous words, which are existing. And how do we do that? How do we do that? We do it in this way. This is as before. This is as we had before, but we have plus m here. I define this matrix M, whose ijth element
it's n by n, and whose ijth element is like this. When j is less than or equal to I, the element is 0. It means that it doesn't have any effect, so it is attention. However, for j greater than I, it becomes minus infinity. What does it mean? Put minus infinity in this equation. It is inside softmax. So this term is in the power of e, exponential operator. E to the minus infinity becomes 0. 0. So it means that it doesn't have effect. It disappears. So using this mathematical modeling, we are modeling what? Masking for the future words. Okay? Then, by the way, the idea of masking can be seen as a sparsity. So it's good. Again, because of betting on the sparsity principle, and Occam's razor, because I'm not considering the future words. Where are we now? We are here. What do we do? Again, add and normalization. Again, the idea of ResNet and batch normalization. Then, where are we? We are here. Here. We are here exactly. So, what is this? You tell me. This is multi-head attention, but now it's not self-attention anymore. It's cross-attention. Why? Take a look at the inputs. Query and keys come from encoder, output of encoder. Values come from here, output of the masked multi-head attention after add and normalization. So what does it say basically? It means that how much my output words are attending or related to my input words. You should somehow, for encoder and decoder, you should relate them to each other. This part is relating the decoder and encoder part. It says how much my output words are attending to my input word, the embedding of the input words, the output of encoder, right? Then where are we? Again, we are here. Sorry, here. Then we do add and normalization. Again, ResNet idea and batch normalization. Okay. Then again, we do feed forward, one feed forward layer just for the sake of parameters, right? Learnable parameters. Again, add ResNet idea and normalization. So we are here. However, we have n of them. Again, for this, we stack them n times to have more learnable weights. And n equals 6 again for decoder has been found to be useful. Okay. Then what do we have? A linear layer again for the sake of parameters, learnable parameters, right? A feed forward layer. Then we have softmax. Why? At the end, we have softmax activation function. Why? What is the number of neurons at the end? How many words do we have in dictionary? For example, in English dictionary. I don't know, maybe 10,000 assume, okay? We will have 10,000 neurons at the end. Can you believe that? 1 neuron per word in the dictionary. Why? And by softmax, we'll calculate the probabilities of the words for the next word. Although, as there are very huge number of them, the probabilities will be very small, but one of them will be larger than the other ones, right? And that will be that will tell me what word should I generate as a next word. Do you get it? Usually in NLP models, the output is very huge. The number of neurons in the dictionary, the number of words in the dictionary. You get it? So this was a transformers. In the next session, we will continue talking about complexity of attention compared with RNN, and then we'll talk about BERT and GPT. Just in simple words, you remember transformer was encoder, decoder, right? BERT says only consider encoder. Throw away decoder. That becomes BERT. Transformer says only, sorry, GPT. GPT says consider the transformer, only consider its decoder. Throw away its encoder. And then you make it bigger to have more parameters. So basically, in simple words, BERT is encoder, is a stack of encoders of transformer. GPT is a stack of decoders of transformer. Now I think you understand why ChatGPT generates one word at a time when it generates words for you, it generates words one at a time. This is exactly what it is doing. The decoder of transformer is generating the next word. And it sees the output of the softmax to see what is the next word. ChatGPT is using GPT, which is a stack of decoders of transformer. Okay, we'll talk about it in the next session more. Thank you.